so let's look at an example of exactly that. Let's look at an example of taking an equation, putting it together with the units in order to figure out exactly what it is that we're being asked to find, which in this case is density in grams per centimeter cubed. So we were asked to find the density of a cube that has a mass of 2.69 times 10 to the 5th or to the 5 grams, and it has an edge length of 1 meter. So this is a 1 meter by 1 meter by 1 meter cube or box. So this is like a 3 foot by 3 foot by 3 foot box. It's pretty big. And we might think then that this mass also is pretty massive. But the real question here is not just like how massive is it or how big is it, it's what's the density, right? What is the ratio of this mass to this volume? All right, so we know what the equation to find density is. Density is equal to mass divided by volume. And specifically, the units that we are asked to find density in are grams per centimeter cubed. So this information is going to help us, right, lay out a breadcrumb trail, figure out exactly what it is we are trying to put together. So we need a mass and we need a volume, and that mass needs to be in grams, that volume needs to be in centimeters, right? So if you've learned the like problem solving trick from past experience of like organize what you know versus then afterwards try and find what it is you're looking for. That's kind of the approach that we're going with here. We're kind of laying out everything that we know first. All right, so mass, again, we have picked out or underlined here in the wording of the problem. Our mass, it appears, is already in grams. So when it comes to calculating density, since our mass needs to be in grams, it's as simple as taking that mass and putting it into the numerator of this equation. So 2.69 times 10 to the 5th grams. And we need to divide this by a volume that specifically is in centimeters cubed. Well, we can see in the wording of this problem, we're not explicitly given a volume, but we are given an edge length, and that edge length is in the unit of the meter. So there are two different ways that we can go about solving this problem. Either first, we can take our length, which is currently in meters, we can convert it into centimeters, and then we can cube it. So we can take our length cubed, which will give us a measurement of volume in centimeters cubed, or we can cube the length first, end up with something that is again a length cubed, that's specifically in meters cubed, and then we could convert to centimeters cubed. So there are two different ways that we can go about this, but at the end of each of these branching paths, we're going to end up with a volume that is in centimeters cubed. All right, so the route that I am going to take is going to be the more complicated of these two, since if you can do, and this is more of a personal philosophy, but if together I can show you how to solve the more complicated problem, in theory, you will have the tools necessary to solve the more simple problem on your own. So what we're gonna do is focus on this second branching path. Again, the one that is slightly more difficult. It's not super difficult, but there tends to, in solving the problem this way, be a common mistake that is made. All right, so we are going to take our length and we are going to convert it into a volume. A length to volume calculation just means that we're taking our length and we are going to cube it. So our volume is length cubed. And in order to solve for this volume, then all we need to do is take our 1.0 meters and cube it. Now, something that's really cool about units that maybe you've learned this, maybe you haven't, is we can treat units just like how we treat numbers. So this exponent, this cubed, we can distribute not only to the 1, which we can, that's normally what we see, you're distributing one number to another, but we also distribute it to the unit as well. So this exponent of 3 then means that we are working with a box that has a volume of 1.0 cubed meters cubed, which then simplifies to 1.0 meters cubed. All right, so this volume of 1.0 meters cubed, we could hypothetically, right, this is a volume, we could plug that into our density calculation, but we are not asked to find density in grams per meter cubed, we are asked to find density in grams per centimeters cubed. And so here, this second step is where some folks get tripped up. How do you convert meters cubed to centimeters cubed. Well, the way we do it, I'm going to draw a line here. So we're going to take our 1.0 meters cubed, and we're going to have to convert each of these meters into a centimeter. In other words, this meter cubed, let's see, I actually have a better way to illustrate this. Give me a second to grab my eraser and get rid of this line. Give me my pen back. Okay, good. All right, so 1.0 meters cubed is the equivalent of 1.0 meter times meter times meter, right? That's what it means to cube something. So in order to convert out of meters cubed and into centimeters cubed, we are going to have to convert each of these meters individually to the centimeter. So we're going to take the conversion of the meter to the centimeter, and we're going to talk more about dimensional analysis in a little bit. So bear with me if you haven't seen this notation before, but we are going to convert 1 meter into the centimeter, and we're going to convert our second meter to the centimeter, and we're going to take our third meter, and we're also going to convert that into the centimeter. And there are 100 centimeters in every meter. If we go backwards, just to go backwards, we can see that exactly right here. Right, so there's 1/100th of a centimeter in every meter. And if we invert that, another way to say it is there are 100 centimeters in every meter. All right, so we have converted our first meter, our second meter, and our third meter. And yes, anytime you have any type of unit that is squared or cubed or even the square root, you need to take that into account as you are converting your units. So we have to convert each of those meters in turn, and what this is going to give us then is a volume that is present in centimeters cubed. So numerically, we're going to take 1 times 100 times 100 times 100. What this gives us is a volume that is 1 million centimeters cubed, or 10 to the 6th. So I'm going to include that now in my calculation for density up on top here. 2.69 times 10 to the 5th grams, all divided by 10 to the 6th centimeters cubed. All right, so now we're taking our mass, which again, we didn't have to do any conversions with, it was just straight up given to us. Our volume down below, we converted into centimeters cubed, and now we can actually calculate the density by taking that mass and dividing it by that volume. Our density then becomes equal to 0.269 grams per centimeter cubed. All right, so we're working with these very large numbers, these large masses, or this large mass, this large volume, and at the end of the day, it turned into a density that was less than 1. So as I guess like to give more of a real world grounding for this problem, if we were to take this box, despite the fact that it weighs a lot and is also very large, it would actually float on the surface of water. It would float pretty readily because it is very, very light. It is less dense than water. All right, so as always, this example problem is going to be extracted into a separate side video, so if you want to come back and see this calculation again later, maybe after class or after we've talked about setting up dimensional analysis kind of problems, unit conversion problems, feel free to do so.